Et pour l'illustrer, tu as choisi un logo de l'île sur lequel on va voter.
Vous avez voté, mais vous l'avez oublié. Sans savoir.
Les urnes sont pleines, c'est bon.
C'est là qui a été retenu pour le vote.
Le scrutin a été sans appel.
Ouais, c'est bien ça. Non, mais où, mais.
Faut que je l'envoie le mail. J'ai un mail à envoyer.
Vous l'attendez certainement.
Oui. J'ai envoyé un mail de rappel il y a 2 minutes. Tu fais le battage des bureaux?
En fait, ici, c'est pour le dernier qui rentre dans la salle.
Pourquoi tu es que tu tombes dans la salle parce que.
J'aimerais dire que le beau logo des trois, c'est quand même solitaire.
Non, je suis parfaitement d'accord. Au niveau du tourage, tout ça.
Bah oui. Surtout.
Un vrai logo professionnel. Enfin, deux autres.
C'est une manière.
C'est vrai qu'un café, elle est tatouée, par exemple.
Ouais.
C'est une manière de travailler la frontière entre la lettre et l'espace en dessous.
Oui, un droit et des lignes dégueulasses.
Touré. Enfin, c'est ça, c'est touré ou détouré, je ne sais plus. Touré.
Faire des photos de jour, quoi.
Ouais, c'est la manière de travailler les bords des lettres. Pour les rendre plus visibles, plus artistiques, plus en relief, enfin tout ce que tu veux. Quoi. Par opposition à prendre ta fonte et la coller brute sur un fond.
C'est un peu compliqué. La petite de sol, ça fait référence à nous.
Bah, c'est Linky, la mascotte du LAMS.
Pour laquelle vous avez voté. Vous avez oublié ce vote-là aussi.
Personne ne s'en souvient, c'est marrant ça.
Et pourquoi ça m'a fixé dans le statut?
C'est un ornithorynque. C'est un ornithorynque.
Oui, et alors
L'ornithorynque est la mascotte du LAMS.
Pourquoi c'est pas dingue?
Parce que ce serait trop facile.
Ah, bah voilà.
Et en plus, l'ornithorynque a tellement de propriétés génialissimes, parce que tu savais qu'il avait des cellules de production électrique, il avait un radar interne, il avait des griffes avoinales rétractibles. La plupart des gens s'arrêtent au fait que c'est le seul mammifère vivipare, mais non, il y a bien plus que ça. Enfin, oui. L'autre gauche. Oh.
Okay. So we're going to talk about the manipulability of voting systems. So voting systems are a way to take decisions together. So they can be used in virtually any situation where several agents need to take a decision together. So not only political situation, but also any multi-agent situation. So the story of the theory of voting is a story of paradoxes and impossibility theorems. First, in the end of the 18th century, Condorcet, the Marquis de Condorcet, showed that when you look at the preference of the population, you can have, for example, that more than half the people prefer an option A to an option B, more than half prefer an option B to an option C, and more than half prefer the option C to the option A. In 1951, Kenneth Arrow showed an impossibility theorem about the social choice functions. he showed that it's impossible to have a social choice function that meets a certain set of very reasonable criteria. Then in 1973, Giba and Sadovite showed that any non-dictatorial voting system is subject to manipulation. So I will explain more in detail later. This theorem was generalized in 1977 to non-deterministic voting systems. In the meantime, people thought that maybe complexity, algorithmical complexity, could be a frontier to manipulation. That maybe, okay, manipulation is possible, but in fact, it's very hard to compute the manipulation. In 1991, Bartholdi and Olin showed that indeed for a voting system called single transferable voting, the manipulation is NP-OR.
What is a dictatorial voting?
I will explain later. So, in the first part, I will present globally the framework of voting systems. In the second part, I will present our study of the manipulability of voting systems. And in the third part, I will show that this can be indeed used in a practical example out of the political scope, and especially in a networking case. So, to talk about voting systems, we need to say how we are going to model the preference of each agent. So, this is the framework. We have a set of mutually exclusive options that I'm going to call candidates. It's a finite set of options. And a theorem from 1944 by Bondeman and Morgenstern show that to model the preference of these agents, we can attribute a real number to each option that represents the preference. In particular, when UK is greater than UJ, that means that you prefer option K to option J. So that's not a big deal. But also, these numbers, called utilities, can represent the relative strength of the preferences. Namely, you can choose the UK, UJ, and so on, so that if you have UK greater than a linear combination of UJ and UL, that means that you prefer the option CK to a lottery which gives option J with probability lambda and option L with probability 1 minus lambda. And in fact, choosing such real numbers is unique up to 2 constants. So in our study, we worked about the utility space, which is the quotient of around by these equivalence notions that, okay, if you represent the same preference, so we say that 2 vectors are equivalent. And we show that in this space of vectors, quotiented space of vectors that represent preference, there is a natural notion of shortest path, which gives to this space a natural projective structure. But once you're here, the problem you have is that you have no time distance, so you have no measure. And we need measures because we want to put probability laws over this kind of space. Okay. So, in fact, our contribution was also to show that the only way to put a measure on it, the only way to put a Riemannian structure on this space, in fact, is the scale. In what follows, we will add an information in the system. is that we model also the notion of approval and disapproval. So we have the hypothesis that when uj is greater than 0, the elector approves candidate Cj, whatever that means exactly. So in this new framework, it modifies a bit the utility space, and in that case, the only Riemannian representations are a bit different. It's a family of ellipses. Half for the beginning, but it's easier after. Okay, now to the core of the subject. So, what do we mean exactly by a voting system? So, in a voting system, we have a finite set of electors, n electors, a finite set of candidates, n candidates. Each elector has a set of possible ballots that she can cast. It's not necessarily the same set for each elector. We can have a voting system that is not symmetric. For example, if you have a committee with a president and other members who do not have the same powers and so on. Then we have also a voting protocol, which is a function from this product to the set of candidates. So the voting protocol takes all ballots and gives a result, which is one of the options. Okay, so at this point, we have sets of strategies that have no special properties. We don't know at all which kind of sets can be. And we have a function that gives a result.
Yeah, can you give an example of that?
Yeah, just a slide after. And to introduce the notion of sincerity, we have also sincerity functions that say, okay, if your preferences are such and such, you should vote these ballots. I will give an example. Okay, a very simple example is plurality rule. So in French, it's uninominal à deux tours, un seul tour, pardon. So in plurality rule, each elector, all electors have the same set of strategies, and the set of strategies is simply the set of candidates. So your ballot is simply, okay, I write the name of the candidate on a paper and give it to the control, blah blah blah. Then the protocol itself to determine the winner is, okay, you take each elector's ballot, you count how many votes each candidate has, and the candidate with the most votes wins.
It's not S1 times S2, it's the product of
S1 times S2 times.
Yeah, sorry,
So
times dot.
That's a typo.
Right. And what you're supposed to do if you vote sincerely is simply to vote for the candidate you prefer. So the candidate who has the highest utility for you. So, for example, here we have 100 electrons. We suppose that this first group, they attribute a utility of 10 for the first candidate, utility for 2 for the second candidate, and so on, blah, blah, blah. So, here the first group, they vote for C1, the second group, they vote for C2, the third group, they vote for C3, and since C3 has 40 ballots and the other less than that, C3 wins. Another very simple example, veto rule. So it's exactly the contrary. So your available strategy, again, is the set of candidates, so you vote for one candidate. But this time, the candidate with least votes wins. And what is supposed to be the Smithson strategy is to vote for the candidate you like less. So in the same example, okay, here the first group votes for against C3, the second group votes against C3, and the third group against C2. So C1 wins. Okay, more complicated example. In these voting systems, Maximin and board accounts, your available ballots are members of sigma n, which is the permutation group. So you give an order over the candidates. So you're supposed to give your sincere order of preference over the candidates. For both voting systems, then you calculate the results of each electoral duel, which is, for example, between C1 and C2, you have 65 electors preferring C1 to C2, and only 35 electors preferring C2 to C1. So here you have the first duel, the second one, and the third one. Now, the two voting systems differ. In Maximin, you look at the line with the greatest minimum. So the worst duel for C1 is a win by 60%. The worst duel for C2 is this one, and the worst for C3 is 40. So in that case, C1 wins. And for both accounts, now you calculate the sum of each line, and the candidate with the greatest sum wins. So in this particular example, it's the same way that, obviously, it's not always the same. So I talked about single transferable voting in the introduction, so I will present it now. In single transferable votes, also you're supposed to give your sincere order of preference over the candidate. So I take the same example again. So first, we look at the top candidate for each elector, and the candidate with least top positions is eliminated. Here, C1 is the favorite candidate of only 25 electors, so it is eliminated first. And electors whose top vote was in favor of C1, their vote will be automatically transferred to their second choice, which is in that case C2. Then, if we have more than 3 candidates, we iterate this process each time by eliminating automatically the candidate with least top positions. So in that case, C2. Exhaustive ballot is a variant of STV. It's more or less the same system, but in STV, you give your order of preference, and then everything is automatic. So the poll is automatically we determine automatically the winner. In fact, in exhaustive ballot, you do actually several rounds. So you vote the first time for your preferred candidate, then one candidate is eliminated, and then you vote again for your preferred candidate amongst the ones that are not eliminated. So last example, it's okay for it's clear for STD or bon, supposé que c'est clair. Okay. Last example, approval and range voting. So in approval, each elector has the right to approve or disapprove each candidate. So you vote for as many candidates as you wish, but once for each candidate. in our model, we suppose that you vote for a candidate when she has a positive utility for you, and you disapprove in case of negative utility. So here, for example, the first group of electors, they would vote, they would approve C1 and C2, but not C3. Second group would approve C2, but not the other one. At the end of the day, C1 has 64 approvals, 62, 60, C2, 60, and blah, 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 and C1 wins. Rank voting is a bit different. The principle of rank voting is that you give a note, you attribute a note to every candidate, and simply you do the average. So here in rank voting, we can imagine that members of the first group, they attribute a note of 10 to the first candidate, 2 to the second candidate, and in a sense to the third candidate. Okay, so now I will present some basic properties of voting systems. Okay, historically, one of the first notions is the one of Condorcet winner. So we will say that a candidate is a Condorcet winner if, compared to any other candidate, she's preferred by more than half the electors. So, in that example, we can calculate the result of each duel. C1 has 1 victory against C2. C2 is preferred by 60% of the people to C3. C3 is preferred by 75% of the people to C1. So here, we don't have a Condorcet winner. That's the so-called Condorcet paradox. About the voting system, we will say that it meets Condorcet criterion if, when there exists a Condorcet winner for the preference of the population, then the Condorcet winner is elected. So, here's an example about plurality rule. So here, C3 is elected because C3 is preferred by 40 people. But in fact, with this structure of population, C1 is the Condorcet winner. So plurality rule does not meet the Condorcet criterion. It doesn't guarantee that Condorcet winner will be elected when it exists. Okay, so individual manipulability. Getting closer to the subject. In fact, the notion of individual manipulability is more or less exactly the same that Nash equilibrium. So we will say that there is a possibility of individual manipulability when an elector can change her ballot so that she can get better results in the end. So here's an example with border counts, so we'll go a bit slower. Okay, we have only 3 electors this time. Okay, the E1 and E2, they prefer B to C, C to A, and candidate A to candidate B. E3 prefers A to C to B to B. Okay, so for border count, we calculate the matrix of the duels, and V is the sincere winner, if everybody votes sincerely. So V has 7 points, and C 6 points, and blah, blah, blah. Okay, so E1 and E2 is perfect for them, because, yeah, anyway, these are their favorite candidates. Okay, from the point of view of E3, okay, it's not possible to make A win. It's too difficult. But they can think that if C was let's say it would be better for them because they prefer C to V. So what they can do is, okay, get C on top instead of A, which changes only the result of the dual between C and A. Here it will be 3, 0 instead of 2, 1. So it's already better for C. And what they can do also is putting V at the bottom of their balance. So, okay, which changes only the result of the dual between V and V. So now instead of 3 against 0, it's only 2 against 1. At the end of the day, V has only 6 points, C 7 points, and finally, it's enough, C wins. So the only elector, E3, who changed her ballot to vote unsincerely has an advantage to do that. Yes?
It means that E3 has to know that voting
yes.
until of equality, and then you have to do that.
Exactly, exactly. That means that we look at the worst case. The worst case is when the manipulator has perfect information and non-manipulators, okay, don't try to get the initial result back. Okay, so, but, yeah. So generally we will say that a voting system is susceptible to individual manipulation if in some situations, that means when the preference of the populations are such and such, there is a possibility of individual manipulation. So we have just seen that border rule is susceptible to individual manipulation. Of course, it's not always true. If all electors have the same preference, there is no reason for individual manipulation. Another notion, and this will answer your question, is the notion of dictatoriality. So, more or less, the idea is to say that only one elector has the power. But more exactly, it's that an elector can cast her ballot so that whatever the others do, she is able to make any candidate win. And we will say, of course, that the voting system is dictatorial if there is a dictator. So, the important theoretical results for our work is a theorem by Gibar and Saversweis. And okay, any voting system with at least 3 eligible candidates is either susceptible to individual manipulation or dictatorial. Which is by the
you choose also the number of electors?
for any number of electors.
Whatever the number of electors.
Yeah, you fix the number of electors, and for this number of electors, you know that no voting system will be okay.
If there are 1 million electors, it will decide. The dictator decides.
Yeah, so that means that whatever the number of electors is, you cannot choose a non-manipulable voting system.
No, the alternative is that you can manipulate various situations. There are situations where one individual elector can change the result.
You have 1 million electors, you choose their preferences so that
you can choose that.
Yeah, that's it.
Well, it means that you cannot guarantee that you have the institution that you need to.
In other words, yes.
Yeah, but the dictatorial is more difficult, right? Because you mentioned that in the dictatorial case, the dictator can elect the candidate.
Yes.
Can you give us an example of how this will happen?
Simply, if we decide that we have a free option and I decide, this is a dictatorial voting system.
But what we are saying is that you can manipulate an system to become a dictator.
No, not at all.
If you can't manipulate it, then it's dictatorial and vice versa.
In fact, In other words, any voting system except dictator is manipulable. But no, because if I am the only one to take the decision, I have interest to say my real preference, and your preference you can say whatever you want anyway, so it doesn't matter. Okay, so this is very bad news. And in fact, if you choose a non-deterministic voting system, it's not really better.
It is so bad. It's really the worst case.
Yeah, of course. I mean, that's precisely our question. Okay, so the question is, okay, we know that we can find some structure of preference so that the manipulation will be possible, but how often does this happen in real life? So that's our question, and the subject of the second part. Okay. Just before, I've just talked about individual manipulability, but indeed we can expect that if you have 1 million electors, you need to be really close to a tie to be able to have individual manipulation. So you can hope that it will be a very rare event. But our concern is also about collective manipulation, because if electors can discuss between them and decide a strategy together, that can lead to manipulation even with very large populations and also with very small populations. So what we will focus on is coalition manipulability. So exactly the same. Now it's an equivalent of strong Nash equilibrium. So a subset of electors can blah 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 get a better result by lying. And individual manipulation is just a particular case, in fact, of CM. So any non-dictatorial voting system is coalition manipulable, is susceptible to coalition manipulability. Okay, just a quick example. Here with the plurality rule, so the uninominal and tour in French in the text. Here we have 40 votes for C, 35 for C, V, C, 25 for A, blah blah blah. So candidate B wins. Now if this group, if they decide to vote for C, okay, now C has 60 votes, and C wins. And indeed, this group of electors, the liars, they prefer C to V, so they want to do this. In fact, as you notice, it's a bit more complicated than that, because, okay, in real life, are you going to have such good information about all the other electors with votes and so on and so on? Will you be able also to communicate between the members of the coalition and so on? So what we have looked at also is, can you have a coalition manipulability that is easy to put in practice? So an example of this is what we call the trivial manipulation, which consists of using trivial strategy. Intuitively, trivial strategy, just what you need is to know what candidate is the favorite candidate. So what candidate is going to win if everybody votes sincerely. And starting from this, what we are going to do is to say, okay, the candidate I want to manipulate for is my preferred candidate, even if it's not true. The sincere winner is the worst candidate, even if I don't think so. And for other candidates, I keep their respective positions in my preferences. So, for example, if my sincere utility are 1 for C, 2 for E, minus 2 for B, minus 1 for B, I will act exactly as if I think that C has an infinite utility, even if, in fact, here, C is not my favorite candidate, it's A. But maybe I think that A has no chance of winning. So we try to manipulate for C. So I will say, okay, plus infinity for V, I will act as if V is the worst candidate, and for E and B, I simply keep their respective position. So this is the general process. And for each particular voting system, for example, if I'm supposed to give my order of preference, I will say, okay, C first, A second, B third, and V the last one. If I'm asked to vote by approval, I will say, okay, I approve C and disapprove everybody else, and so on. You can adapt to everybody's system. So now what we call trivial manipulability is simply to say, okay, we have the Simstar winner who is V. If all electors who prefer C to V use the trivial strategy, as we have just defined, then C is elected. If that works, in that case, it's very simple to give voting advice so that there is manipulation. So I'm not going to give an example because all the previous ones were in fact trivial manipulation. So I will give an example where it doesn't work. This time I will use the veto rule. So that, which is, okay, you vote against your least preferred candidate, and the one that is that has the least vote wins. So if everybody votes sincerely, here they vote against C, and these two groups they vote against A. So the candidate V wins. Now, if all electors preferring C to V, namely the second and the third group, if all of them they use the trivial strategy, then they will act exactly as if C is on top, which is already the case, but also V at the bottom. So they will all vote against V because they fear that V wins. But in that case, with veto rule, okay, so C has 25 veto, V has 75 veto, so A wins, which was not the goal. And especially the manipulators, they preferred V to A. So it's really a failure because the result is worse for them it's worse than the initial result. But here, in fact, if they are a bit more clever, they can manipulate. If they divide into two, part of them voting against A and part of them voting against V, then C has only 25 vetoes and C wins indeed. So in that case, CM doesn't work, but there is a possibility of coalition manipulability. Okay, another variant which differs more or less the same goal, which is, okay, can we have a simple manipulation? Is what we call unison manipulability, which means, okay, if we all prefer a challenging candidate C to the Simstar winner V, can we decide together the same ballot? We are going to cast the same ballot, so that C can be elected. So, in that case also, most of previous examples were in fact unison manipulability, and a negative example is the previous one. In fact, unison manipulability couldn't work in the previous example. Okay, and now about the information and resistance and counter-resistance. A last notion, and then I will stop, is coalition manipulability that is resistant to a simple counter-threat. Because in fact, what you can imagine is that, okay, we have heard by the polls, by the blah blah blah, opinion studies and so on, that it's likely that V is going to win. Okay, so with a group of people, we prefer another candidate C to V, and we decide a strategy so that we hope that C is going to win. But if electors preferring V to C know that, maybe they will think about the strategy, change their vote sincerely so that in fact V will win. But we can expect that they are going to do this. So we can change our strategy to adapt to blah 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 and so on. So of course this kind of process is very complicated. It's not clear that there is a convergence for this kind of process. And anyway, even if it's the case, we don't want to compute that. So what we do is that we use a more tractable notion, very simple, which we call coalition manipulability resistant to simple interface. So the principle is that you look only the first counter threat and not the response to the response to the response, blah blah blah. We'll give an example. So another example with plurality rule. Here V has 40 votes, A has 30, and C has 30 votes. Okay, but in the proponents of A, there are two categories of electors. Proponents of A who prefer V to C, and proponents of A who prefer C to V. Okay, now if all the electors that prefer C to V, they agree, they can try a trivial strategy, which is, okay, all of them, they will vote for C. So in that case, C has 45 votes, V still has 40 votes, so C wins. So there is a possibility of coalitional manipulation. But if the proponents of V expect this, they can agree with this second group, say, okay, we are all going to vote for V because members of the second group, you really don't want C to be elected. So there can be a counter threat from the electors who prefer V to C, which is simply, in that case, to vote for V. And if they do this, okay, V has 55 votes, so V wins back. So in that case, there is a possibility of coalition manipulation, but in fact there is no possibility of coalition manipulation resistant to simple interface. Okay, quick example. Okay, here there is a manipulation also, and here, in fact, after the manipulation, C has 60 votes, so whatever the others do, C will win anyway. So there is really this manipulation is resistant to interface. Okay. So now I will present what we do about that. So our approach is an experimental approach using computer simulations. What we do simply is that, okay, we draw the preferences of the population according to a given probability law, probability distribution. Mostly we use either a uniform distribution on the sphere, since we have proven that the sphere is a good model for the space of preferences, or also we use a polar distribution centered on one point of the sphere and with a certain concentration. Then, once we have the preferences of the population, we try every voting system that I have presented, so Borda, plurality, blah, blah, blah. And for each of them, we calculate the results, and we evaluate if there is a possibility for coalition manipulability, trivial manipulability, and so on. And in the end, we do statistics about all that. In fact, we do a bit more because we don't only determine if a manipulation is possible, but also in many cases, we determine what is the minimum size of the coalition that can do that. But I will not develop this in this presentation. In this work, one of the problems, I talked about it in the introduction, is that we face many NP-hard problems. And especially for single transferable votes and exhaustive ballots. It was shown in 1991 that determining the manipulation is a problem. And in fact, it's the best known algorithms for exhaustive ballots are a polynomial, blah, 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 times 2 power m. And for SPV, the best known algorithms are in factorial n, m being the number of candidates. So what we've done about this is that we provide polynomial approximate algorithms for exhaustive ballots and single transferable votes in order to be able to do the simulation. Okay, now I will quickly present the results of this simulation. So, first, here I take uniform culture, which means that I draw the preference of each elector uniformly and independently on the sphere of the utility space. I have 50 electors, 4 candidates, and in fact for each, in fact there is 10,000 experiments, and I have 10,000 drawings of the preferences. Here, just an overview of the different criteria, so coalition manipulability, trivial manipulability, unison manipulability, resistance to counter threat, and individual manipulability. What we can see already on this graph is that, okay, for some of the voting protocols, in fact, CM is equivalent to TM or UM. So that's very easy to demonstrate for approval, range voting, plurality rule, and so on. But also for some more complicated voting protocols like border count, in fact, it's not exactly equivalent, but in fact, statistically, it's almost always true that to be able to manipulate, it is enough to know how to trivially manipulate or to unison manipulate. And even for exhaustive ballots and STV, which have the reputation of being difficult to manipulate and so on, yeah, okay, already with trivial manipulation, you can have a great part of the cases. Okay, so trade-off for TM, UM, TMSSA, and IM. Now I will talk only about CM, which is our main concern. Here we can see how the coalition manipulability vary with the number of electors. So here we have 4 candidates, we have the different voting rules, and we plot the proportion of experiments, proportions of drawings of the preferences of the population, where we have a possibility of coalition manipulability. So, what is not very surprising, the more the number of electors and the more the rate of manipulability. And in fact, for most of voting protocols that we have studied, the manipulability tends to 1 very quickly. So very quickly, in 100% of the case, there is a possibility of coalition manipulation. The main differences, yeah.
Here, the distribution you are choosing really for has a great impact, right?
Not so much. Not so much. We will see that in a 3 slides.
If you suppose that you have a peak,
sure.
One of them,
sure, of course, yeah.
You will separate
yeah.
them.
Yeah, I will talk about that in 3 slides.
Okay.
The main difference to what I've said are the veto rule, and we don't know in fact if it increases and go to 1, or in fact if there is another limit. But yeah, Vitor rule is very sensible to the parameters. So this behavior is not necessarily the same with another set of parameters. And the other case is the case of exhaustive ballot and STV. In fact, it's almost the same curve. It's not exactly the same voting protocol, but practically it's the same. So, and we see, for example, with this set of parameters that, okay, even with 10,000 electors, okay, it's manipulable only 30% of the time, something like that. Now, variation of the number of candidates, still with uniform culture for the moment, precise. Okay, as expected also, the manipulability grows with the number of candidates. And in fact, even for exhaustive ballot and STV, it tends to one. Even if they still fare better than the other voting protocols. Now, I know it was only 2 slides. So, we have also studied polar cultures, and the result is very interesting, and we don't understand everything for the moment about this, but more or less, okay, at the beginning, sorry, I need to comment on the parameter. So, lambda is the concentration, so when lambda is equal to 0, it's uniform distribution of the sphere. When lambda tends to infinity, it tends to one peak distribution. So at the beginning, okay, every voting systems are more or less manipulable, blah blah blah. And when you concentrate the population, most of reasonable voting systems, the manipulability tends to 0. With an exception for a true vote, because in fact it's not discriminant enough and actually complicated. And what we wonder is there some kind of phase transition somewhere in here? In fact, okay, for most of the voting protocols, there is a strong decrease, more or less at the same value of lambda. So we wonder if there is a phase transition between manipulable zone and peak zone. And in fact, theoretical considerations tend to show that this phase transition could be around lambda equal to the square root of m. But okay, we still need to do experiments about this to see if it's really like it.
What was the definition of lambda, sorry?
It's a concentration parameter.
Right. What is the concentration point?
Think of a Gaussian distribution. It's a kind of Gaussian distribution.
Yeah, but so what does it mean? I mean, are you a prediction for the candidate?
No. You choose a distribution of preferences, and this is the center of your Gaussian, and then you have a distribution around. So first you choose a random set of preferences, and then you take a distribution centered around these central preferences.
Okay, so.
Okay. Just a second. Okay, so it's in fact a probability distribution on the sphere, so on unit vectors. Okay, so you choose a pole, which is one unit vector, okay, x0, and the density of probability around the vector x is proportional to the exponential of minus lambda x,
So that's
the scalar product x0.
That's x0, which is the parameter.
Yeah.
Okay,
Yeah.
so what is it?
In fact, for this experiment, each time we draw a population, first we draw E0 randomly, uniformly on the sphere. Okay. And then we draw each elector independently according to this law. That's what we do exactly. Does this answer the question?
Okay, so then the question comes back. How sensitive is the experiment to this way to the polarization? You go from a uniform one to a polar
very
right?
thick one, right? Yeah.
Yeah. But how sensitive is this result, this state, to the way you select the distribution, which is the one that indicated here? You can choosing another function here, right?
Okay, I understand. In fact, this distribution, which is called von Mises-Fischer distribution, is exactly the equivalent of a Gaussian in a Euclidean space, which means if you have one fixed mean and a fixed standard deviation, in a Euclidean space, the distribution with optimum entropy and respecting this mean and this standard deviation is the Gaussian one. On a hydrosphere, it is this one. So in fact, it's once you have a center and concentration, it is the distribution where you add the least information to the system.
But you may have two poles.
Yeah, we do that also.
3 poles.
But this is out of the scope of the presentation, but we do that also.
But the intuition is that you have one main opinion on multiple poles and some noise. And the Mises-Fischer distribution is used to model the noise around the consensual opinion.
Yeah, it's supposed to be I mean, it shouldn't be so manipulable. If you have a pole, you expect that it's not.
Yeah.
If you add more poles, you expect that.
Degenerated is more manipulable.
But for most voting systems, if all electors have strictly the same set of utilities, you have no manipulation possible.
Yeah, except for approval and blah, 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 and so good. Yeah. But we do that also, and in fact, we also use other kinds of distributions to determine the consensus. So I just present these two ones for the presentation. Okay, now very quickly we are going to see an example of application to a networking case, which is the problem of establishing an end-to-end path from an ingress carrier to an egress carrier. So here we show an example of how such a network can be organized. And okay, we have a demand, which is, okay, I want to establish a path between this node and this node. So how are we going to do that? And here we are going to do the assumption that the electrons are the carriers themselves. So they can give their opinion about which path is the best one, and of course which one is the best path for them. The candidates will be the possible path. In fact, we are not going to take every possible path because there are too many, but we are going to limit to a given number of hops beyond the minimum number of hops. And, okay, what will be the preferences of the carriers? The assumption that we are going to make is that, okay, if the path doesn't come by me, I don't care. I don't lose money, I don't gain money, whatever. But if a carrier participates to a path, then this carrier will have a financial reward, and we suppose that there is a fixed financial reward which is equally shared between the carriers participating to the path. And each of them have also a cost, depending on what is the previous node in the path and what is the next node in the path. So in that case, the problem for them is to optimize the path minimize the cost, and in fact, in the end, to maximize the average financial gain.
You are doing this for one new path or globally for the whole set of paths that are required? Are you doing this, your optimization?
Yes.
Are you doing this for one new path that is requested, or globally for the whole set of paths?
In fact, we do this for a pair ingress-egress, and for such a pair, we do a vote, and a path is chosen. Now, if I take another pair and I want to establish an end-to-end path for this pair, I will do a new vote and
from scratch.
And from scratch, yeah.
Okay. Usually this is not the
No,
way it works.
the model is not taking into account the already existing path. It is a simplified model.
Yeah.
There is no limit in capacity taken into account and so on.
Okay.
It was just to see what it gives.
Okay, so in that case, sorry.
But even if you don't take into account the capacity, but just the reward,
Yeah, the reward, yeah.
you may like to...
But the reward is independent of the number of paths already existing, and so it's a kind of memoryless somehow. So you just need to consider each possible pair of ingress, make the calculation, and
So you may, that's my fault.
C'est lui qui faut.
So I didn't understand, because if you want to earn money, you will try to push other parties to go to you, right?
Yeah. Yeah.
Except if for a given path, the cost is greater than the financial reward that you are going to have. So, for example, if you're, I don't know, like Italia, and you're asked to make a link between Iceland and Greece, maybe you don't want to do this directly.
There is a cost.
Yeah, sure, of course. So, for this kind of problem, the most natural idea is to use range voting, because range voting does precisely what we want, that is maximizing the sum of utilities. So, the problem of range voting is that, according to our simulations for this specific problem, so, according to our simulations for this specific problem, range voting is manipulable nearly 100% of the case. So, what it means is that some of the carriers have interest to lie in order to have more path and earn more money, and etc. Of course, the financial gain is optimum, but it is optimum only if everybody votes sincerely, which is likely not to be the case. So, according to what we've seen before, an idea to solve this problem is to use single transferable votes, since we've seen that it's not as manipulable as the other voting system. And in that case, STV is manipulable between 15 and 31% of the case. It depends on the exact set of parameters, because we take parameters for the cost function and blah blah blah. But yeah, more or less it's around 20%. And so, and the question is, does it find as often the greatest path? Not so bad. And most of the time, it finds a path that gives a financial income that is more than 80% of the optimal one. So that's it. I don't want any missile anymore. So in 3 words, I hope that I have convinced all of you that voting system can be thought of for any kind of situation when multiple agents want to take a decision together amongst a finite set of options. In finite, it's a bit more complicated. We also, this way, answer a question about algorithmical complexity, because is it really a barrier to manipulation? In fact, no, because most of the time, trivial manipulability is enough to manipulate. And we have shown also that, okay, even if all voting systems are susceptible to manipulation, some are really better than the other ones, and especially there were already some results in the literature suggesting that maybe STD would be better than the other ones, and our simulation confirmed that it's the case. Now for the future work, we still have a lot to do to analyze the results of simulation, because in fact, of course, it's much more than I have shown to you. We use other kinds of distribution, multipolar distribution, also some kind of distribution based on other geometrical models and so on. And we have also a lot of analysis to do about the minimum size of the coalition when there is a possibility of manipulation, which we calculate already also. We have also an idea of future work about a new voting